Well, it's been a characteristic of of this course and the textbook to take some time to compare and contrast different theories. This puts a focus on what's similar about them, what's different about them, and so we appreciate the general principles involved as well as the specific differences between them. And I want to spend a little bit of time doing that now for special versus general relativity. And then I want to turn to a couple of modern topics, which are quite perplexing. Okay, the cosmological constant and dark energy. And we'll get there in a moment. Let's start off with just some observations about the theories we're talking about. Special versus general relativity. Okay, well, special relativity, of course, we know what the symmetries are. We know what we're trying to include. Okay, we spend most of our time discussing inertial frames of reference. Okay, because in inertial frames of reference, we have simple equations of motion. We generalize the Newton's laws that apply in inertial frames of reference to relativity in such a way. And the symmetries, well, we consider a space which is uniform and isotropic. So translations in space-time are symmetries. Okay, we didn't discuss this very much in our case, but it was certainly there. Rotations are symmetries. Our space is isotropic, Minkowski space. We have special relativity, and that gives us 3 parameters there for the rotations around the 3 axes. And then, of course, our favorite, the boosts, the Lorentz boosts. They can be done as well. Okay, and I have a little. I don't know how to count. Apparently, there are 10 symmetries. There are boosts in the x, y, and z direction. There are 3 of them. Okay, so I have 4 plus 3 plus 3, and that's 10 as far as I know. And boosts, I was getting carried away there. But the boost is spatial. Okay. General relativity comes along, and it talks about general coordinate transformations, general coordinate covariance. So it makes these symmetries local, okay, and considers general coordinate transformations. So now the theory of gravity has much more symmetry. You can change your coordinate systems in a space-time dependent fashion. So you might have your space-time everywhere, and then you make changes, rotational coordinate changes over here, okay, and a week over there, okay. So they're space-time dependent. Okay, these then become the principle. These are invariance principles, and they dictate the character of your dynamics, as we have seen, right? As we've seen in general relativity, we have our transformations were space-time dependent, and our theory had to respect those symmetries, and that told us what our observables could be and what the symmetries of the observables were as well. Led to the equivalence principle, which made general relativity inherently nonlinear. Led to the idea that all forms of energy momentum attract one another. Okay. In particular, gravity waves carry energy momentum, but they attract one another. So in the field theory, unlike in Newton's world, where the theory is linear, this theory is intrinsically nonlinear. Okay, and the force that generates the attraction between mass points, old-fashioned mass points, now attracts one another as well. Well, is this really all that special? Well, I want to tell you that modern quantum field theories are based on local symmetries as well, and universality principles as well. So they have a great deal in common with general relativity. In particular, the theory of colored quarks and gluons. Okay, well these are field theories that live in Minkowski space. Okay, they don't affect space-time gravity. Okay, and in most of the applications, you're working in Minkowski space. It's an excellent approximation to what's done in national labs in where quantum chromodynamics is studied, and collisions at the Large Hadron Collider at CERN and places like that. Okay, but there is a local symmetry in these theories. It's not space-time. Okay, where these theories combine quantum mechanics with special relativity, not general relativity. But the local symmetry is an intrinsic symmetry of the system. In the case of quantum chromodynamics, it's the symmetry called color. The quarks carry color, and the gluons, the quantum that provide the force between the quarks, also carries color. The quarks carry color in the fundamental representation, and quarks in the adjoint representation, quarks in the three-dimensional representation, and gluons in the eight-dimensional representation of color. And the color symmetry is SU3. So perhaps you've heard these words before. I hope so. And if you study modern field theories, you'll learn about that in a great deal more detail. Now, there was something about general relativity. It's very special. That general relativity is sensitive to the 0 point of the energy scale. Okay, we didn't discuss this as we were flying through it. Okay, we introduced the energy momentum tensor. We illustrated it with a couple of simple examples. If you take a full field theory course of general relativity, you'll get into T mu nu in much more detail. But it depends upon T mu nu, not the difference of potentials like Newtonian physics. Okay? Okay? This is energy momentum. It's not energy momentum differences. So you have to ask yourself, well, what is the 0 point of energy? Well, in quantum field theory, you would say, well, that must be the vacuum energy density. Okay? And in a classical field theory, that sounds terribly trivial. That's the nothing there. But in the quantum field theory, that's a bubbling mess. Okay, the vacuum is full of quantum fluctuations apparently, and they show up very importantly in theories like quantum electrodynamics. It's okay. We can apply external fields to an otherwise empty space-time and pop particles out of the vacuum. Okay, so it's real stuff. Okay, the vacuum has real potentials, and you describe those processes with covariant amplitudes called Feynman diagrams, and when you make collision processes, some of the particles taking part in those processes might be those you might associate with a vacuum, okay, and some of those being associated with the particles themselves. Okay, if you have colliding protons, for example, the structure of the vacuum and the structure of the particles themselves get all mixed up, and you have to understand the whole totality. Okay, vacuum fluctuations contribute to the vacuum energy. Okay, vacuum fluctuations have frequencies or frequencies that go from 0 to infinity, or size scales that go from 0 to infinity. So it sounds like understanding the vacuum energy, instead of in classical physics there's nothing to do, in quantum physics there's everything to do. You have to understand physics at every length scale from 0 to infinity. So it's a ill-posed problem. Maybe there's a symmetry principle that tells you what it is, or maybe there's something wrong in this formulation. We're barking up the wrong tree. That's a possibility as well. But certainly, naively, and from the perspective of quantum chromodynamics or quantum electrodynamics, a full understanding of vacuum fluctuations implies a full understanding of physics from size 0, microscopic, to macroscopic. Okay. It's something we don't really understand it, but we might want to parameterize it. And we parameterize it by saying that there's a contribution to the energy momentum tensor, which goes like G mu nu. That's the only tensor available for the vacuum. Nothing there. Sounds compelling, maybe not. That the T vacuum goes like G mu nu with a coefficient that I call the energy momentum density of the vacuum. Okay. Okay, so it's the vacuum. If you have a particle, you have a preferred direction where it's propagating, or you have other properties, preferred 4 vectors to make T mu nu out of. If I have the vacuum, what do I have? Well, I just have space-time. So the only metric, the only tensor I would have available to describe the vacuum is G mu nu. If I have matter around, I have a full T mu nu full of properties of electromagnetism or massive particles, but in the absence, I just have that. And this is therefore called dark energy. Okay, it's just a vacuum contribution. We don't understand it much, but let's parameterize it and see what the experiment says about it. So if the T-vac has this form, I have to put it into the right-hand side of my Einstein field equations. I write it like that. Other people try to pull this onto the other side of the equation, and they write it as Einstein tensor minus lambda G mu nu is equal to the T mu nu of massive fields, or electromagnetic fields, the fields that characterize external sources. And lambda is called the cosmological constant, and it's related to my previous definition of rho vacuum with a factor of 8 pi g. Okay, we don't understand either. They're proportional to one another. Okay, from observational cosmology, however, comes an estimate for the vacuum energy density. It's on the order of 10 to the minus 12 GeV, which in terms of MKS units, CGS units, is 10 to the minus 8 ergs per centimeter cubed. It's an incredibly tiny amount of energy on the scales of quantum field theory or quantum chromodynamics or electrodynamics. This is negligible on the scale of galaxies, but important on the scale of the cosmos. Okay, that's important here. We're introducing a basic energy scale into a theory, and the theory has been well tested. Okay, so this thing better be small enough that it doesn't mess up general relativity in our applications to the solar system, for example. It better not contribute to the precession of the perihelion of Mercury, for example, or in the lensing of light as it goes around the sun. Okay, so it has to be small like that, and we'll see this number is sufficiently small that it satisfies that. But it is important on the scale of the cosmos. This comes out of the observations of distant supernova. Okay, this is the discovery of dark energy. This is the discovery of the fact that the cosmos expansion is accelerating in time. Okay, this led to a famous Nobel Prize by observational astronomers. Okay, you can look into the textbook for the details of that. Okay, so let's try to see if this energy density makes sense in size. Okay, that's the first thing to do. It's funny numbers here. It looks very small. 10 to the minus 8 ergs per centimeter squared. My goodness. What would we guess for it on the basis of dimensional analysis and the knowledge of quantum field theory? This is a property of the vacuum. My goodness. Okay, it's non-zero, but it's very, very small. Classically, I would have put a 0 in there, but it ain't true. The basic constants are, if I go to quantum field theory, are Planck's constant, the speed of light, and Newton's constant. And from those constants, I can make a basic energy called the Planck energy, and just do the dimensional analysis, and you see that h bar c to the 5th over Newton's constant to the square root is an energy called the Planck energy. It's huge, 1.22 10 to the 19 GeV, which is 1.95 times 10 to the 16 ergs. Okay. So now, by dimensional analysis, this is this rho vacuum is the energy density per 4 volume. Okay. So I would, if I was just doing dimensional analysis, I would take the basic energy in the theory, which is the Planck energy. That's the only energy I can sensibly make out of the constants given. There might be some coefficients here of pi or something. I can't talk about them. I can only discuss the gross features of this thing. But I would put in EP to the 4th. Well, EP to the 4th, as you can see here, is of order 10 to the 112th ergs per centimeter cubed. Okay, we wanted to get an answer that was 10 to the minus 8 ergs per centimeter cubed, and we were wrong by 120 orders of magnitude. Okay. It's not that we're a little bit wrong, it's like we're completely in left field, okay? We're off by 120 orders of magnitude. We have no clue, this argument, to this. In fact, you could argue with a number like this that the entire universe would shrink down to a tiny object on the basis of the amount of curvature that it would suffer. So there's something terribly wrong in all of this. And I'm not going to bias you by saying where I think it might be, because I'm probably wrong. Okay. Okay. So for the moment, we just have to accept that there is such a thing. Maybe our incorporation of it into the theory is wrong, but certainly what is not wrong is that the universe is expanding at an increasing rate. Okay, and let's show that. Let's show that it implies the expansion of the cosmos is accelerating. And I'm just going to do this in the context of a simple Newtonian model, and more sophisticated considerations can be made. But really, we don't really have a handle on all of this. Let's just get a feeling of it in a naive way, because I think that's good enough. We'll take the Newtonian limit of the field equation with a cosmological constant in it. Well, that's easy. We know how to do this, right? We've done this many times over, and I'll just keep this guy around for fun. Well, it's clearly just going to modify the source term, okay? Bringing in a minus sign because I'm going to the spatial pieces of the Poisson equation, and it goes like lambda, and it'll pick up a factor of c squared. Okay, when I keep track of my factors of c. Check well, you can do this, right? Because you know that what comes into the right hand side is 4, 5 over c squared, and c squared is 4. But it's also discussed in detail in the book and in the supplementary lectures. Okay, well, if that's the new equation, okay, I can get you the gravitational acceleration outside a mass of order m, because I know that the gravitational acceleration is the gradient minus the gradient of the potential. Okay, so I'll take that particular situation, okay, where I have, where v, okay, where v, perhaps I should be writing phi, where v is given by the potential due to a mass m, and I'm going to account for this particular term, and I see that taking the gradient of v, where the Laplacian of v has a term that goes like lambda c squared, means that the acceleration has a term which goes like lambda r in the direction of r, right? Because if I go over here and take the gradient of this thing, then this will become a constant. Okay. When I take the gradient, only the derivative in the r direction will contribute. Okay, wiping out this r and r dotting into the gradient will just be 1. Okay, and so I see as advertised, as advertised, that this term gives me a force which is repulsive, radial, and grows with distance. And let's not do too much damage to Columbus Moon, and put the r squared into the force law. Okay. Okay. So we find a universal acceleration outward that grows with distance. Okay. The observation value of lambda is so small that the effect is negligible on the scale of the Earth. You have to put the numbers in to see that. Solar system and galaxies, but it's not negligible on the scale of the cosmos. Theoretical puzzle. Why is lambda different from 0 and yet so small? Okay. So that's one of the big puzzles of the field, which people are trying to grapple with. Another thing people are trying to grapple with, of course, is the unification of gravity with quantum mechanics. That's also a difficult problem, for which there is no solution. Okay, remember, we know how to merge quantum mechanics with special relativity, given the field theories that are so successful these days, like the Standard Model and others. But we don't know how to do that for gravity. One of the problems we come into in those considerations is the question of probability conservation. One of the central points of quantum mechanics, that probability is conserved. because if you're in the vicinity of a black hole, which seems to suck things out of the universe and never lets them back in, it isn't clear that probability is conserved in those situations. However, when you start merging the ideas of quantum mechanics with black holes, you find all sorts of new phenomena. You find something that's called the Hawking radiation, okay, that in a vicinity, that if you take into account the quantum vacuum, okay, that in the vicinity of a black hole, you'll find a degree of radiation of particles at a particular temperature. Okay, and so black holes are not really black in quantum field theory. They have a particular temperature, and they radiate the temperature. In practical terms, it's very low, but these are matters of principle. Okay, and so some of the phenomena that we've learned about classical black holes that seem to be well supported by experiment are challenged when you try to unify the theory with quantum mechanics. You don't know how to write down a full quantum mechanical theory, but you can do specialized calculations like the Hawking calculation of the temperature of a black hole, and you find very interesting indications of unified physics there, but the full picture is not available. Okay, whether a complete unification is possible or whether there will be an information crisis or not is not really settled. Okay, and it's the type of things that folks are working on very hard at this time. Okay, so we'll leave it here, and then next time we'll start picking up on our special topics. Okay, we have a whole bunch of them. I call them special topics simply because they go beyond a lot of the material in the textbook, but they're covered in the supplementary lectures, and they're all covered in supplementary lecture 11. I want to look at some of those things, like accelerating clocks. I want to look at rotating black holes. I want to look at velocity-dependent effects in the vicinity of a rotating black hole. These illustrate some of the concepts that we've dealt with in the course, and there's lots of stuff that we can do, which is very interesting, very timely, okay, and will help us understand the theory better in both fundamentals and in applications of it. Because remember, we want to understand the theory well enough so that you're empowered to do thinking for yourself and can contribute to the field. This is not a course of an encyclopedia character where there's lots of facts. More or less, what we're trying to do here is to do the elementary side of the theory, so that you have complete grasp over every bit of it, and so you can take it and run with it. Okay, till next time.